Science fiction writers have long used our neighboring planet Mars as a setting for their tales about other beings. Scientists, too, theorized about the possible existence of life on Mars. Through telescopes, astronomers many years ago saw markings on the planet which some believed were canals crisscrossing the surface. A few people thought the canals had been constructed by intelligent beings. Later, we found that the markings called canals were really artifacts of perception and did not exist. But scientists were still tantalized by color changes on Mars, which some theorized might be vegetation blooming in warm months and becoming dormant during colder times. I'm Larry Ross, Director of Space Programs at NASA's Lewis Research Center in Cleveland, Ohio. This is the 7th episode in our series of 13 programs called Journey Through the Solar System. Now we're going to see a film called Mars, The Search Begins. The film documents how fact began to replace speculation.
From the earliest history of mankind, there's been a bright red speck of light in the night sky called Mars. For the last few hundred years, we've known that it's a planet, a place more or less like our own, a world in its own right. But a detailed knowledge of what Mars is like had to await the mission of Mariner 9, an unmanned spacecraft which went into orbit around the planet Mars in late 1971 and worked for almost a year.
A geologist looks at a planet to first understand the processes that are going on there, the things that are affecting the development of its surface at the present time. But even more important, we try to look back in the past to place the events that have taken place over a long period of time, to understand what happened early in its development, in the middle part of its development, the things that are happening now, and to predict what might happen in the future.
For a biologist, one of the great scientific opportunities of our time is the search for life on Mars. That question is so important, it will change our whole concept of life. It will change our whole concept of how life originated. The question is not only whether there is life on Mars, but whether that life has a separate origin from our own life, life as we know it.
When Mariner 9 was placed into an orbit around Mars, it saw a planet 1/2 the size of Earth, blanketed by a gigantic dust storm. For almost 2 months, scientists could see only blurred pictures of the top of the storm, or the ice and snow of the South Pole shining dimly through the dust, and several dark spots, apparently mountain peaks protruding up through the storm. And then the great clouds of dust receded, and the long weeks of frustration ended with one magnificent and exciting word: volcanoes. The photographs bear little witness to the violence in which these volcanic mountains were born. On Earth, the eruption of volcanoes created the atmosphere and produced the water that fills our oceans and rivers. On Mars, the same magic of physics and chemistry created a thin alien atmosphere and provided a source of water on a planet known to be drier than the Sahara. The exploration of Mars by early mariners photographed about 10% of the surface in brief encounters as they flew past the planet. But it is Mariner 9 that explores all of Mars and reveals a planet beyond speculation. The intricate spacecraft, operating at a distance of over 100 million miles, is commanded by a complex system of men and machines on Earth. 6 mission experiments yield results that can be woven into a total picture of the planet. As the spacecraft orbits Mars, the density of the atmosphere is measured by radio waves as they pass through the atmosphere on their way to Earth. The thin Martian clouds are scanned in the infrared to determine if they are carbon dioxide or water. An infrared instrument continually measures the changes in surface temperatures, ranging from minus 150 degrees Fahrenheit on the night side to as high as 70 degrees at noon on the equator. The height of mountains, the depth of canyons, and the gases in the Martian atmosphere are measured by invisible radiation in the ultraviolet and infrared wavelengths. Analysis of subtle changes in the orbit of Mariner reveals that Mars has an odd bulging shape, and this shape is a new clue to its internal structure. 2 television cameras photograph and map the surface of Mars. In nearly a year of operation, they transmit more than 7,000 photographs. Of these, over 1,500 are specifically taken to ensure that the entire Martian surface will be mapped. The photographs are carefully matched, precisely positioned on a globe, and skillfully fitted together. This shadow on the surface of Mars is cast by one of its 2 moons, Phobos, only about 13 miles long. The second moon, Deimos, is even smaller. They are the darkest objects ever photographed in space. Primitive chunks of rock battered by meteoroids, their origin is unknown. This is the face of Mars, photographed by earlier mariners. Here, a visitor might think he was on our moon, that this planet, too, was unchanging and dead. But transported to the other face of Mars revealed by Mariner 9, he would see fresh evidence of a living, changing planet. The old craters here have been long since covered by immense flows of lava. Thin white clouds form and drift across the dark blue sky. In the distance, he would see the long, gentle slope of a great volcano. Intense, small dust storms scour canyon walls into sharp ribs of ancient rock. Near the poles, he would see a great series of ancient terraces, each layer composed of a mixture of dust and snow deposited by the wind. Each took thousands of years to form. Each is an episode in the history of the planet.
The exciting thing that we discovered, there were many of them, but one very exciting thing that we observed in the middle of the mission was that things were changing before our very eyes on the Martian surface. For example, in 13 days, an area about 7 miles across discontinuously appeared, just hadn't been there before, suddenly it was there. Now that kind of change had been observed, but from the Earth and on a larger scale, for 100 years. It was called seasonal changes, and the early observers imagined that there was plant life on Mars, and that in local spring and summer the plants grew. They darkened the landscape and heightened the coloration of the landscape. Well, we proposed before Mariner 9, my colleagues and I, that instead what was happening was that there were high winds that were uncovering the dark material, dark rocky stuff, by blowing off bright, fine particles. And the changes that we've seen on Mars happen during the course of the mission are consistent with this kind of idea. So it looks as if the seasonal changes of Mars are not due to biology, but due to weather. We calculate that the winds are maybe as much as 200 miles an hour in such a storm. And so you have to have very high winds to make that thin Martian atmosphere pick up fine particles from the surface. So while most of the time it may be nice and calm, there are storms which are much more violent than any we see on the Earth. Now, if you have very fast winds, picking up all this fine-grained sand, that's a source of erosion and abrasion much more serious than any wind-blown erosion we know about on the Earth. It breaks things up, makes things collapse. It also picks up things and denudes landscape of overlying sand and dust. It's an exceptionally dynamic environment. In some respects like the Earth, in some respects quite different. It's its own planet. There are old parts of Mars which are cratered by hunks of rock falling down into Mars and making holes. In some of those craters, there are these strange black splotches. At least some of those splotches, on closer inspection by Mariner 9 cameras, turn out to be vast sand dune fields. Another indication of wind-blown sand and dust on Mars.
There is a similar dune field in the Mojave Desert in Southern California. That is, the overall form of the two fields and the height and spacing of the larger dunes are alike. However, the complex pattern that we see here shows that the wind directions change frequently. On Mars, the wave pattern indicates a consistent wind direction.
Here is an astounding feature which no one expected on Mars. An enormous rift valley, almost 3,000 miles long, comparable to the largest such feature on the Earth, a sign of great geological activity.
In this model, the flat surface of a large Martian plateau is cut by the Great Rift. A smooth sloping ravine drops abruptly to the bottom of the canyon 4 miles below. The small peaks on the canyon floor were once part of the plateau surface. Today, this great fracture in the crust of Mars is 75 miles across. The original fault has been widened and shaped by various forms of erosion. Great landslides are triggered by quakes that shake the crustal rocks. Wind-blown dust strips the receding canyon walls. Some side canyons may have been deepened by running water. Melting of underground ice, followed by slumping of walls, further erodes the great fault. This rift valley, of which we have seen only a small part, is so huge that it would span the United States. And the Grand Canyon of Arizona would fit inside one of the smaller tributaries.
And as another and even more spectacular sign of geological activity on Mars is this enormous volcano, hundreds of miles across. It's the largest volcano in the solar system so far as we know. It's a young object because it doesn't have very many impact craters in it, meaning that geological activity on Mars has been occurring in very recent times.
This is a model of the volcano. Its base measures 370 miles across, and the peak stands 15 miles above the plain. The flanks of the crater bear the familiar tortured patterns left by violent eruptions of molten rock. The walls drop steeply to a scarred, blackened floor. Frozen lava lakes marked with rough circles where the interior fires of the planet forced their way to the surface and built a mountain. This is where the atmosphere of a planet is born, in searing heat that transforms solid primitive rock into thin vapors. Today, the crater looks dead, frozen into a rigid page in a textbook on the evolution of a planet. This is not an old volcano. To a geologist, it is young, and no one can say if it is alive or dead. In this volcanic field near Flagstaff, Arizona, there are hundreds of volcanic vents, some as old as 2 million years. The youngest of these, Sunset Crater, is similar to the small volcanoes we see on Mars. And the lava flows are the same as those we see on the flanks of the larger volcanoes. I'm standing beside the basaltic lava flow that comes out of Sunset Crater, and the great jumble of blocks that you see here are caused by the fact that the lava comes out as a liquid, but it chills on the outside, and the interior of the flow keeps moving, and it breaks up the outer edge into this great mass of jumbled blocks. It's very similar in size and form to the lava flows that we see on Nix Olympica on Mars. In many Mars photographs, we see long, sinuous ridges that go across the great lava plains. We're sitting on a feature that's very much like those. We think the way this feature formed is that the still liquid lava down in the center of the flow keeps exerting pressure. It lifts the top up, finally breaks it, and then squeezes out through the frozen crust.
And here is something which no one guessed would exist on Mars at all. This is one of hundreds of little channels. This is actually not so little. This is a few hundred miles long. Channels which look for all the world as if they've been cut by running water. Here's a close-up of the inside of one of those channels, and it has the characteristic patterns of terrestrial stream beds. The trouble is there isn't any liquid water on Mars. The pressure on Mars is so small that it can't keep a lid on liquid water. If this is due to running water on Mars, it must have been made at a time when the Martian climate was very different from what it is today, at a time when Mars had much more Earth-like conditions.
This is a model of a section of a 3-mile-wide channel north of the Martian equator that seems to be formed by a broad flow of liquid water. It is similar to drainage channels on Earth that are fed by rainfall. Parts of this channel also show evidence of wind erosion and softening of contours. The islands appear to be similar to sandbars formed by rivers on Earth. They might be heavy gravel or perhaps solid rock.
I personally don't see any escape from the idea that running water is what carved out those channels. But if that is the case, then we must imagine that Mars was one time, not so long ago, very different from Mars today. Right now, we have a Martian atmosphere which is thin, the surface which is cold. But when those channels were cut, if they were cut by water, and I think they are, then you must have had a much thicker atmosphere, much warmer conditions, and a lot more water around than you have today.
Volcanic eruptions are the source of water on Mars. With each eruption of lava, water vapor is spilled out in the atmosphere. It is stored in two different ways.
The first way is in the residual polar cap. This is the North Pole of Mars, and the cap shrinks down to about 5 degrees. It starts at the end of winter, almost 50 degrees across, and we think that polar cap is very thin carbon dioxide ice, and it shrinks very quickly to this little residual cap, and we're still debating as to whether that's water ice, carbon dioxide, or dry ice, or a mixture of the two. The second way that it's stored is in these regions where the frost has disappeared from the surface, but we think it's still stored underground as permafrost, that is, water frozen into the pores of the rock. we were able to photograph several different kinds of clouds with Mariner 9. This photograph is of one of these clouds. It's the edge of the North Polar Hood. It covers the whole northern region of the planet, and this is the southern edge of the hood. Here you see an ice-rimmed crater and the clouds that form downwind. By measuring the temperatures and the elevation, we're able to understand the composition of these clouds. This particular cloud, the temperature was critical, and we know that it was made of dry ice or carbon dioxide ice crystals. Near the great volcanoes, we saw clouds that were much lower and much warmer. We also got spectral lines that proved that these clouds were composed of water ice crystals.
Just as the study of the climate of Mars should, I think, help us understand the climate of the Earth, I think the study of the biology of Mars will help us understand the biology of the Earth.
The big question for the biologist is, what is life? What do we mean when we say life? We're really only familiar with one form of life, terrestrial life.
Terrestrial life, life on Earth, carries a trademark revealed by biochemical analysis. All living things on Earth are composed of combinations of molecules, some as simple as water, which is fundamental to life as we know it, others of great complexity. One of these combinations, protein, forms the enzymes that direct the complex chemistry of life. Another, nucleic acids, are genes contained in chromosomes, the basic unit of life. These combinations of molecules distinguish living things from non-living systems. One other element needed to make a living system work is a method of reproduction. DNA is a molecule containing the genetic message, the blueprint for future generations. This genetic code is the same for all living creatures, for all life, which means that there is really only one form of life on Earth.
If there is life on Mars, then there will be a simply fabulous expansion of the perspective of the biologist. Because all the organisms on the Earth, even though they seem to be different, are fundamentally the same. Their chemistry is all identical. And they're just wrapped in different kinds of wrappings. Us bacteria and us people and us plants, us protozoa, we're all the same on the inside. Now the question is, are Martian organisms the same on the inside as us? Is life everywhere, does it have to be the same as us? Or are we just one example of a vast array of possible kinds of biochemistries? Well, there's no way for us ever to answer that question, no way for us to determine the generality of life on Earth, except by looking for life elsewhere. And the nearest candidate planet is surely Mars.
We're not quite sure how to search for life on Mars. We do the obvious. Microorganisms, the small creatures, are always associated with higher forms of life. So it's microorganisms we're searching for. A small microbe could adapt itself possibly to the cold Martian winter, to the dry Martian summer, to hostile Martian atmosphere, or even to the sub-zero temperatures of the Martian night.
This is a full-scale model of the lander spacecraft. This device contains a 10-foot extendable boom. It reaches out, picks up a soil sample, and returns it to an instrument inside the spacecraft, which will then perform 3 life search experiments. The first experiment will assume that Martian life is similar to Earth life. It uses Martian soil and Martian atmosphere. The soil is soaked in a liquid containing a large quantity of water with a mixture of foodstuffs used by microscopic life on Earth. If Martian life forms eat the nutrients, they should excrete gases in the process, as do microorganisms on Earth. This will change the gases in the test cell. Any changes will be detected and will be evidence of life processes. The second experiment is half Martian and half Earth. The soil sample is moistened with only a little water containing foodstuffs that scientists think exist on Mars. The foodstuffs are tagged with radioactive carbon-14. If life processes take place, then carbon gases released in the process will contain the radioactive tracer and can be detected. The third experiment is based on Martian conditions. It uses Martian soil, Martian atmosphere with scarcely any moisture, to which is added radioactive carbon gases, and simulated Martian sunlight, minus the ultraviolet radiation. If Martian life forms are growing and multiplying in the Martian soil, it is assumed they would use some of the Martian atmosphere in the process. The atmosphere, tagged with carbon-14, should be metabolized into the bodies of the life forms. After allowing time for life processes to take place, heat will be used to break down solids into gases. Detection of carbon-14 in those gases will be evidence of a life process.
It always happens in the history of science that as your perspective broadens, you learn more about what you left at home as well as what you went out to seek. And so it may be that in the long term, the greatest boon to science and to mankind from the exploration of Mars will come in terrestrial biology. It's just a speculation on my part, but I think there's a good chance that that will be the case.
We have seen the planet Mars, in one sense, for the first time through the eyes of Mariner 9. And it was not quite what we had expected. How can a planet bear the scars of great raging floods and the gentle tracing of rain when liquid water on its surface vanishes into thin vapor or congeals into solid ice? The possibility now of large amounts of frozen water on Mars may hold the answer to one of man's basic questions. Has life developed only on Earth, or is there life elsewhere?
The possibility of life on other planets intrigues us all. The search for life on Mars continued in 1976 when 2 Viking spacecraft, launched by the Titan Centaur, landed on the Red Planet. We will review the results of those missions during our next episode, Life on Mars. Until then, this is Larry Ross saying goodbye from NASA's Lewis Research Center in Cleveland, Ohio.